When we began the discussion about covalent bonds, we talked about how the electrons were shared. Well, one thing about the sharing of electrons is that not all atoms share equally. Another way to phrase that is when they're in a bond, not all atoms have the same attractive forces for those electrons that they're sharing. We call the attractive power or the atom's attraction, it's electronegativity. So electronegativity is a measure or a number of the atom's attractive power for the electrons in a bond. So basically, this number tells us how much that atom likes to attract those electrons in a bond. So when we're thinking about it, there's going to be numbers. I'll show you on the next page. But the higher that number is, the higher the electronegativity value what it means is that it wants or attracts the electrons in the bond more. Okay, so the higher the number, the more attracted that atom is to the electrons, or the more attractive it is. So here's a table from the book. It only shows the main group elements. The transition elements would here in the middle would have some, but they don't have quite the same trend. So if we're looking, you can see as you go across from left to right, the electronegativity value gets larger. And as we go up the table from the bottom to the top, it also increases, leaving fluorine up here with the highest electronegativity value. And in the opposite corner down at the lower left, rubidium, potassium, these have the lowest. So fluorine has the highest attractive power to the electrons in a bond, where the metals in general over here have the lowest. Now, if we think about even back to ions, metals like to lose electrons and nonmetals like to gain them. It has to do with their attractive power. The nonmetals in general have higher attractive powers. Now, you may notice that the noble gases don't have electronegativity values. And if you kind of reason through it, noble gases in general, we don't expect them to form covalent bonds or to form bonds because of the octet rule. It helps us predict that they are already very stable. So they don't have electronegativity values because I guess you could think of it, they're not going to share the electrons because they're already stable. Now again, chemistry is full of surprises, and if you studied chemistry more, you would discover that some of the bigger, larger noble gases will form bonds. So there's always new things to learn in chemistry. Let's go back to the first page now that you kind of see these numbers, and these are not numbers you memorize. So let's look through these notes. So here, so before I go over there, so let's look at this example right here. So above the element, if hydrogen has an electronegativity of 2.1, which I read from the table, and chlorine has an electronegativity of 3. So the larger number, chlorine, is attracting the electrons. So what we would see is the electrons would shift and be more toward the chlorine. So if we think of the electrons as a cloud, the electron cloud would be a little bit bigger around the chlorine because it has more attractive power. So see here it says electrons are attracted more to chlorine. Why? Because it has a higher electronegativity value. Now another notation, there's this little squiggly, which is the Greek lowercase delta, and I have it here. This one has a negative and this one has a positive. The delta means, here, look here, delta negative means partially negative. Well, that's because electrons are negative. So if you see the electrons getting more around the chlorine, they're going to get negative. That leaves less cloud around the hydrogen, and it's going to be positive. So you can see a delta positive means it's partially positive. Now it will always be that the element with the higher electronegativity will be negative, and the element with the lower electronegativity will be partially positive. So here's another example. Let's take a look at it. So again, looking up the electronegativities on the table, and let me just show you. So N 3.0 and carbon 2.5. That's where those numbers are coming from. So in this case, nitrogen right here has a higher number. So that means the electrons will be drawn toward the higher electronegativity, the higher the number. And that means the nitrogen will become a little positive. If we thought of the bond, the electrons would be a little bigger around the nitrogen. This is an electron cloud. And then that makes it negative, and the carbon would be positive. So here's that electronegativity table. And so where this leads us is to distinguish between bonds that share equally, share unequally because their electronegativity values are different, or can't share at all and instead transfer. So what we have a few words here that we need to look at, and here's two of them, polar and nonpolar. So polar or a polar bond means there is a separation of charge. Now another way of saying that is that the electrons are shared unequally. So the separation of charge, or what's also called a dipole, is when we get the partial negative and partial positives in the bond, right? Because now you have a little charge there. So in polar bonds, this is when the electrons are shared unequally because you have a difference in electronegativities. If you put the word non in front of polar, then it means not polar. So nonpolar bonds, they don't have a separation of the charge. The reason is their electronegativities are so close, they share equally. So polar bonds, the electrons are shared unequally because they have different electronegativity values. Nonpolar bonds, the electrons between those two elements are shared equally because their electronegativity values are very close to each other. So as a general rule, we can use this table here below to kind of help us predict what type of bond would form. So we can look at the electronegativity difference, and you can see if it's, the first one says here, if it's less than 1/2, 0.5, then we consider that it is a non-polar bond, and what that means is that it's shared equally. If the difference is at somewhere from 0.5 all the way to 1.9, we say that that is polar. And what polar means is because they have different electronegativities, they're shared unequally. Both the first two scenarios are covalent, which means the electrons are shared. But in Chapter 3, we know that there's some bonds where the electrons aren't shared, they're ionic. Well, when the difference between the electronegativities, like between metals and nonmetals, gets so great that the electrons aren't even shared at all, then it causes the electrons simply to be transferred. So how do we use this information? Well, one thing we can do is if we're asked to classify bonds, we can look at the difference in electronegativity between the two elements to see what type of bond it is. So here you have two chlorines, so that would be a chlorine and a chlorine. And we don't really care what kind of bonds, we're just looking at the two elements. So looking back at the table, chlorine is a 3.0. So this has a 3.0 and this has a 3.0. So if you take the difference between the two, it is 0. So they have the same electronegativity. Look here, if it's less than 0.5, which 0 is, this is a nonpolar bond. So Cl2 contains a nonpolar bond. Now, what if they give you CCl4? Well, CCl4, I really just need to look. It's a carbon in the middle with 4 chlorines. And they're not asking me about all of them. They just want to know about one of the bonds. So I say a carbon and a chlorine. Well, we just saw chlorine was 3.0. Carbon is, right here, 2.5. It's always a positive difference, so whichever one is bigger. So I subtract the 2, it's 0.5. Looking here, if you're between 0.5 and 1.9, you're considered polar. So this is a polar bond. Now, oftentimes, I'll ask you which one would be negative. Well, the one with the higher electronegativity is always partially negative, and the lower electronegativity is always partially positive, because the one with the larger number draws electrons toward it. Now here's water, and again, it's not asking you about the whole thing, it just wants to know about each bond. Well, this has an oxygen and a hydrogen bond, right? Water is like this. So I don't have oxygen or hydrogen. Let's go find them. Oxygen is a 3.5 and hydrogen is a 2.1. So 3.5, 2.1. So to figure out 3.5 minus 2.1 is what, 1.4? And looking back, if I'm between 0.5 and 1.9, I am polar. Now, which part of this would be negative? Well, the higher electronegativity is always the negative one, and the lower is always the positive one. Okay, and so let's do the last one. We have NaCl, so just thinking about it. Chlorine I know is a 3.0 from a previous problem. Na is 0.9. So it's always a positive number, so just take the bigger one minus the little one. This is 2.1. So we notice anything that's greater than 1.9 would be classified as ionic. And this makes sense for us because the metal, this is a metal and a non-metal, which that makes sense. We would predict that that one would be ionic.